Section 1.6 probability. Define the probabilities for independent, dependent, or compound events and represent as a fraction, decimal, or percent. Experimental probability. The experimental probability of an event is the ratio, and let's define it by that ratio. Here we have P, which means probability. The event would be, for example, if I want a heads while I'm flipping a coin. There are two possible outcomes. I could either flip and get a heads, or I could flip and get a tails. Therefore, what I want is the number of times the event occurs. Well, if I want the probability of a head, that would be one time that I could get a head if I flip it. How many possible outcomes could there be? There could be two possible outcomes. Therefore, the probability would be 1 to 2. I just need to define the event, and that will give my probability when I generate this ratio. Our first example. A basketball player made 32 free throws out of 50 attempts. Find the experimental probability that the player makes a free throw. Well, we want the probability, P, of the event, which is free throws made. I'll just shorten that up to be FT for free throws. And what we want to do is generate that ratio. The total number of possible outcomes is the number of free throws he tried, which means the number of free throws that he made, and also the number of free throws he didn't make, which here is defined as 50 trials or 50 attempts. Now what we want is the number of free throws that he made. That's the event that we're trying to get, which is 32. Now all I have to do is to determine the probability is to simplify my fraction. Here, when I divide by 2, that's going to give me 16 over 25. And that is the probability of hitting free throws for this player. What I could do is even specify further to actually give this a decimal. If I take 16 in a calculator and divide by 25, that's going to give me 0.64. I could go further into the problem and actually generate this into a percent by multiplying by 100, which would give me 64% of the time this player makes free throws. But in this problem, all they wanted to find was the probability of the event. Our next example. A long jumper reaches a distance of 8 feet, 12 times out of 20 jumps. Find the experimental probability he will jump 8 feet. Let's set up our probability P. The event that we want to occur is that he will jump 8 feet. And now let's set up our ratio. The denominator is the total attempts that he tries to make his jump, and here it's defined as 20. And how many times that event that he jumped 8 feet actually occurred, and here it is 12. Now all I do is simplify to find the probability. Here I'm going to divide by 4, which is going to give me 3 over 5. Again, I can take this further, even though this is our solution. The probability is 3 times out of 5 that he will jump 8 feet. But I can set this into a decimal. 3 divided by 5 gives me 0.60. I can also find the percent that he will jump 8 feet. And that is going to be, when I multiply by 100, 60%. Simulation. When actual trials are difficult to conduct, you can find experimental probability by using a simulation, which is a model of one or more events. Let's take a look at a simulation. Suppose you take a true-false quiz and guess 4 answers at random. What is an experimental probability that you will get at least 3 correct answers? Number 1, you have a 50% chance of guessing a solution. Just like getting a heads or a tails, you could pick and get a true or a false. Next, how could you get a 50% chance outside of a true-false quiz? Let's look at 2 examples. 1, I could flip a coin. And if I let heads be correct, then tails would be incorrect. So if I would flip heads, 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 tails, I would then get a solution of 3 correct in a row and then a false. But I would have to try that many times. We could also let even numbers be correct, or we could let odd numbers be incorrect. And again, I could just generate sets of 4 numbers and see which ones are even and odd, and then determine how many are correct. Number 2, in the problem 4 questions were guessed. We must generate 4 outcomes to choose from. Well, how can we do that? We could flip a coin 4 times to generate a heads or a tails. For example, the previous one was heads, 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 tails. Then I would have to flip 4 more times and 4 more times after that to generate groups of 4 and then determine how many heads would get me 3 solutions or more. Or I could have a computer generate groups of 4 numbers, in other words, a 4-digit number, and then have that determine how many even numbers are in each group to determine how many are correct. 3 even numbers in a group or more would give me correct. Any more than 1 odd would be getting 2 or more wrong. Number 3, how many times would give a good result? The larger the better. No smaller than 50 in our choices. If I have a computer, 1,000 would be great. Let's see what a simulation would look like. So if I took a coin and flipped it 4 times, and this was my outcome, and then I did that 4 more times to get an outcome, 4 more times, all the way down. Now, like I said before, I need to do this many, many times. 50 would be the smallest number of times I should do it. A computer, 1,000 or better. So in this situation, I got 3 heads, which would give me 3 correct answers. Here, again, 3 correct answers. 1 correct answer. 1 correct answer. None. 2 correct. 2 correct. 2 correct. And 3 correct answers. And another 3 correct answers. So what's the probability of getting 3 or more correct? Well, I add up the number of total times I flipped the coin per group of 4, which is 10 groups of 4. Then, how many had at least 3 correct answers? And that gave me 4. Therefore, when I simplified, the probability was 2 out of 5. Or when I changed to a decimal, 2 divided by 5 is 0.40. And multiplying by 100 gives me 40% chance of getting at least 3 answers. We know our chances have to be a lot smaller than that, or we would probably guess, but we don't want to do that. If I had a computer generate numbers at random, then they would generate a 4-digit number at random. And again, my evens are my correct, my odds are false. So therefore, on this situation, I get 2 even numbers, therefore I got 2 out of 4 guesses. 1, 2 out of 4, 3 out of 4, 3 out of 4. Here, again, 3 out of 4. On this problem, I have 1 out of 4, 3 out of 4, 4 out of 4, and 2 out of 4 correct answers. So what I want is the probability of 3 or more correct solutions. And when I add up the total possibilities, I have 10 4-digit numbers. How many achieved 3 or more correct solutions? That would be 5. Here, my probability would be 1 out of 2, or 0.5, and multiplying by 100 would give me 50%. This example is very similar to the last one. Describe a simulation you could use that involves flipping a coin to find the experimental probability of guessing exactly 2 answers out of 6 correctly on a true-false quiz. We're going to choose coins here because you could get a heads and a tails, which is 50%, just like true-false. So we have to identify heads could be correct, tails could be incorrect solutions. So if we flipped the coin in groups of 6, we could end up with heads, tails, tails, heads, tails, tails, which would give me 2 correct solutions. That's what we want to exact. The next one would give me 1 correct solution. This one would give me 4 correct solutions. The only one that presents the event that we want would be the first one. Again, we'd have to run this simulation many, many times to get an accurate probability of selecting 2 correct answers out of 6. Definition. The set of all possible outcomes of an experiment is called the sample space. Theoretical probability. If a sample space has n equally likely outcomes, and an event A occurs in m of these outcomes, then the theoretical probability of the event A is m over n. For example, find the theoretical probability of rolling a multiple of 2 with a number cube. Notice we can roll our cube and get multiple results. What they're asking for is a multiple of 2. Well, on a die, how many ways can you get a multiple of 2? That would be 6, 4, and 2. So there are 3 ways to get a multiple of 2. 3 different outcomes when you roll this dice will get me a multiple of 2. How many total outcomes are possible? Well, there are 6. So what we want is the probability of a multiple of 2. And that would be the number of ways I can get the multiple of 2, which is 3. Outcomes would give me a multiple of 2 out of a total possible of 6. Therefore, the probability of my event occurring, which is the multiple of 2, is going to be 1/2, which we could simplify to a decimal to be 0.5, which could be, when I multiply by 100, 50%. The next problem, they want us to find a theoretical probability of rolling a multiple of 3. Well, how many ways can I get a multiple of 3? Those numbers on a die for a multiple of 3 is either going to be 3 or 6. So there are 2 ways to get a multiple of 3. Total possible outcomes is still going to be 6. So the probability of a multiple of 3 is going to be 2 over 6. In this case, it would be a probability of our event occurring in this situation, multiple of 3, when I simplify, 1 out of 3, which could be 0.33 as a decimal, or 33%. If a jar contains 4 pennies, 5 dimes, and 9 quarters, you pick a coin from the jar at random. Then they want you to find each theoretical probability. Here, the event that I want is the probability of selecting a penny. Well, recall from our example, n is the total number of items or choices available. Here I have 4, 5, which is 9, 9 plus 9 is 18, and m is the quantity available for the event that I'm choosing, which is a penny. So there are 4 pennies inside the jar. So the probability of selecting a penny is 4 out of 18, or when I simplify, 2 out of 9. Again, I could change that to a decimal, then a percent if needed. Next, what is the probability of selecting a dime? Again, my total possible outcomes is 18, but the total possible outcomes to selecting a dime is 5. Therefore, the probability of selecting a dime is 5 out of 18. Probability of not a penny. That means I can select a dime, a quarter. They just don't want a penny. My total possible outcomes is still 18. How many ways can I not get a penny? That would be to add 5 and 9 together, which is 14. Then I would simplify, and that would give me, when I divide by 2, 7 over 9. What is the probability of selecting a dime or a quarter? Here, I have a total possible of outcomes, 18. Selecting a dime and a quarter is 14. When I simplify, that's going to be 7 over 9. So notice the last 2 problems are exactly the same, but they're stated differently, but they're asking for the same solution, or basically the same event. The last one, what's the probability of a penny or not a quarter? So here, what they're asking for is a penny, and what else is not a quarter is a dime. So my total possible outcomes is 18, and a penny and a dime add to 9. Therefore, when I simplify, that's going to give me 1 out of 2. Our next example, they want us to find the probability that a beanbag lands at random on one of the following rings. Well, what's the procedure to do this? Number one, we have to find the area of each ring and of the total 3 rings. So the way I started was area of ring 1. We know that the area of a circle is pi r squared. The area of ring 1 would be pi x squared because the radius is x. That is what I have listed A1 to be. A1 equals pi x squared. The area of ring 2 is going to be the area of 2 rings minus the area of ring 1. So the area of the 2 rings put together for 1 and 2 is x plus x, or 2x, listed here, and the area of ring 1, which we found above. So when I simplify, that's going to give me 4 pi x squared minus pi x squared, which gives me the area for ring 2 to be 3 pi x squared. The area for ring 3 is rings 1, 2, and 3 together, minus the area of ring 1 and 2. And that will leave us, getting rid of 1 and 2, 1 and 2, will leave us ring 3. So the area of all three rings, 1, 2, and 3, is going to be x plus x plus x. That's the radius, which is 3x. And the radius for ring 1 and 2 is going to be x plus x, which is 2x. When I simplify, that's going to give me 9 pi x squared minus 4 pi x squared, which is 5 pi x squared. And of course, the area of the total, using the radius of each ring, which is x plus x plus x, gives me 3x squared, or 9 pi x squared. Our first event is to find the probability of landing in ring 2. What I need is the area of ring 2 over the area of all the rings. So the area of ring 2 is 3 pi x squared, and the total area is 9 pi x squared. So I substitute in area of ring 2, 3 pi x squared, over area of the total rings, which is 9 pi x squared. When I simplify, the pi's cancel and the x squareds cancel. So I just simplify the constant, which is going to be 1/3, which is the probability of landing in ring 2. What is the probability of landing in ring 3? I need the area of ring 3 and the area of all the rings together. The area of ring 3 is 5 pi x squared. Substituting 5 pi x squared over the total, which is 9 pi x squared. That gives me, when the pi's and the x squareds cancel, a probability of 5 to 9. Now I want the probability of landing in ring 2 or 3. Therefore, what I need to do is to find the sum of areas of ring 2 and 3 over the area of the total. The area of ring 2 and 3 added together is going to be 3 pi x squared plus 5 pi x squared, which is 8 pi x squared, over 9 pi x squared, which, when I simplify, is going to give me 8 to 9.